All right. Good afternoon, everybody. How are you today? So I need your attention, please. So today we're going to have our last lab for this semester, and we are going to do the calculation or determination of the molar mass of unknown volatile liquid using the ideal gas law. So I put together the whatever we learned in the lecture, which is how to calculate pressure or volume or amount of the gas using the ideal gas law. As you can see here, we also were able to rearrange it. So then we will be able to calculate the molar mass or the density or a volume or whatever, any one of those variables. Now also we should know, everybody should know by now, that the way that we are going to measure the number of moles, which is part of this variables here for the property of the gas, is by dividing the number of gram, in other words, the mass of this substance divided by the molar mass, right? So if we have one component or one metal or one element, the molar mass of, or atomic mass of that element. If we have compound, then it is the molecular mass of that compound or substance. So then we are able to substitute this particular value in the ideal gas law. And then after that, which is as you see, these are the incronym for mass, which is in gram, and molar mass, which is gram per mole. Now, we can always rearrange this equation, so then we will be able to have a possibility of calculation for the molar mass of our compound. Could be unknown, could be given to us, but this is how we are going to rearrange the ideal gas law, so then we will be able to solve for any unknown. And this is going to be the rearrange. So the molar mass will be equal to the gas constant times the temperature, which should be in Kelvin, as we all know, as long as it is dealing with gas, divided by the pressure, and then multiplied by mass over volume. You see, when we rearrange, so the mass over volume will give me density. We should know that, right? Mass over volume is equal density. So why don't we put density instead of mass over volume? So in your calculation, in the data sheet, they want you to calculate the density of your unknown. Your unknowns, we have 3 of them. We have A, B, and C. At the top of the data sheet, it's asking you to identify the code of your unknown. Whatever you're going to pick under the hood, as we always have them, those chemicals are volatile. Be careful, they are written. Hopefully we are all having our mask, but we also need to have our goggles all the time. All right? And then you're going to pick one, and you stick to it because we need to have it more than once. One trial, it's more than one trial, okay? So, once you are going to do the volatile, and I'm going to talk about the experimental procedure in a minute, but anyway, at the end of the day, since we know that mass over volume equal density, today you are going to measure the density in gram per liter, not gram per milliliter. Why? Why do you think we have to do it in liter, not in milliliter? Yes, Kyle?
So that it's universal or just
universal according to R, right? R is a national, international system unit, that it has to be in the volume in liter, the temperature in Kelvin, the amount in mole, and the, what else? The volume liter, and pressure should be in ATM, right? We all know that. That's why we're going to measure the density in gram per liter. And this is how we are going to get our own last, value. So we also going to convert, as we all know, the degrees Celsius with our thermometer, because that's how we are going to measure the temperature. in degrees Celsius converted into Kelvin by adding to the, like the differences between the scales, which is 273.50. Also, I measured the pressure for today in Newark, okay? And it was given to me, like, you know, online. If you go online, you will see it also. It is 30.20 inch mercury, okay? And it is also given to you, this formula here, in your introduction of the experiment. So we need to convert, because we are having R, which is pressure should be in ATM, right? Atmospheric pressure. So we have to convert whatever's given to us in the water cask into the ATM. And this is the formula. So the pressure for today in inch times mercury. Everybody with me? So this is the formula. 30.20, multiply it by 25.4, which is this is the conversion factor between the two. You see the equation, and this is the equality. 1 inch mercury is equal 25.4 torque. So I multiplied by 25.4 torque, divide by 760 torque, that will give me the ATM. So the pressure has to be measured in ATM. Okay? That's given to you. All what you have to do is to do the calculation and then find the pressure in ATM. All right? So we're done with the temperature, with the pressure, and then we want to make it ready for our own, like, you know, the rest of the steps in the experiment. I also tried, I mean, I don't know if you can see that, over there is, like, you know, the apparatus. So you see the rail is there, and I'm going to get you the hot plate. You need the hot plate also. You're going to have a beaker, right? You are going to fill it to the half with water, tap water. And then we are also going to give you an Erlenmeyer flask. In the Erlenmeyer flask, you are going to put 8 to 10 of your, 8 to 10. You're going to put 8 to 10 milliliter of any of those three unknowns that it is under the hood. So we're going to add about 8 to 10. And we are going to cap the Erlenmeyer flask with the foil, with aluminum foil. And then we have pins. You just pin it and to make a hole, okay? So, and then we start heating, okay? Now you also need to have a thermometer, okay? Thermometer. And the thermometer has to be also clamped to the rail here. Make sure that the bulb, the bottom of your thermometer doesn't touch the bottom of your beaker. Okay, so therefore we need to clamp it to let it stay, like, you know. Yes, submerge in the water, because we're going to measure the temperature of the water. You don't put it inside the flask. No, it is outside in the beaker, because we want to measure the boiling, like, you know, temperature of the water. But don't let it touch the bottom, okay? And then we're going to start. Inside the flask also we need to have the boiling chip, so it doesn't, like, you know, splash. So we do have everything here. And then we're going to start boiling or start heating. When you start heating, you are going to see that the inside is going to start bubbling until it is done. It's done, completely done. You remove it and put it under the tap water running, okay? So what are we trying to do here? Can somebody tell me? Why do you think we have to take that immediately when it is done? There is no liquid anymore. When you don't see it in your naked eye, and you do not observe any liquid inside the Erlenmeyer flask, remove it immediately. And we do have the rubber handle, because be careful, this is very hot, right? We remove it, we hold it, and then we put it immediately, just like the body of your Erlenmeyer flask, not the neck, because you don't want to put water here. just like tilted, and then put it under the running water cold. Cool it down, you're gonna see there will be what? What's gonna happen? Anybody could know, telling me? What are you gonna see?
Like condensation?
You're condensed, absolutely. Nathan, the condensed liquid, because it was a vapor, right? When we heat it. Now, when you heat it, you know, the reason why we put the, like, you know, the aluminum foil, so we try to get hold of the liquid. But when you heat the air inside the Erlenmeyer flask, we are going to, what? Get rid of all the air, the vapor water, okay? And what you have there on the top of the, in other words, that it is going to take the volume of your Erlenmeyer flask is the gas of your liquid, right? It's gas. It's because it is volatile, so probably around maybe 70 to 80 degree Celsius. Those are going to start, like, you know, converting from liquid to gas. When we try to cool it down, we bring the vapor liquid into a liquid, back into a liquid. And then after you do that, let it run under the water for like, you know, maybe a minute or so. You clean it. You are going to dry it with a paper towel. Dry the outside body of your flask and take it back also to weight it. Take it to the balance and weigh it. Now, before we start everything, we are going to take the empty Erlenmeyer flask. We put a couple of these, what do we call them? Boiling chip, all right? And we should have a foil, aluminum foil. We're going to cap it with the aluminum foil. And as is, when it is empty and doesn't have any of the liquid that you want to measure, you take it with the foil, with the capped foil, and then you measure it when it is empty. You keep it in your data. After we're done, and then we condense the liquid back and cool down, you take it back and weigh it. You need to take off the volume the weight of the like, you know, everything that you have, which is the container, the foil, and also the boiling chip. Because we don't need it. We need only the condensed liquid of the volatile gas, okay? So this is what we're gonna do. Once you are going to be done, this is gonna be the mass, right? Of the condensed. That's the mass of your unknown. How about the volume? Now we know when we are going to heat the liquid, what is the volume of the liquid? It's going to be after you heat it.
Equal to the container.
To that container. That's absolutely right, Sarah. So what do we have to do? After you're done, because we need to have 3 trials. If we can finish with 2 trials and you have good result, you're okay. But if you have any doubts, you can do the 3rd trial. As you can see in the data sheet, you have 3 trials. All right, so after we're done with the 2nd trial, you're going to remove the stone, remove the foil, and then fill it with tap water under the rim of the Erlenmeyer flask, and then with water, just tap water, and then you are going to measure how many mil is this. That's the volume of your. That's the volume of your unknown, so you can find the density. And maybe from the density, we're also going to be able to, what? Predict what we have from the density when you're going to calculate. Not even that. Once you found this value, you can always find the molar mass of that particular compound, okay? So this is basically what we are going to do today. Is everybody clear? Do you have any question? Like, I know I will keep going on, and if you have any, issue, try to come and ask me, okay? So basically, this is what we are going to do today. This is the apparatus that we are going to use for today's experiment. The measurement of the molar mass of unknown volatile liquid. So as you can see, this is how we set it up. We have the beaker, and then we're going to put the Erlenmeyer flask. We're not going to submerge it all the way, no. It's like just a tip of it, and we're gonna boil the water, and then we're gonna measure the temperature at the time when all the liquid inside the Erlenmeyer flask will be evaporated. We're gonna take it, remove it from the heat, from the water, after we measure the temperature at when it was evaporated totally. And then what we are going to do, we're gonna take that and then we put it under the tap water. We're going to have a tap water running. So we will see that the volatile, in other words, the vapor is going to be condensed back into the flask. We take the flask, remove it from the water, we're going to clean it, right? And then we're going to dry it. We're going to dry it, and then we're going to take it back, and then we try to weigh it over here with our own balance. And then before we started all together, we also, when it is empty, we weighed the Erlenmeyer flask, the boiling chips, and the capped foil. After we condense the vapor of the volatile liquid, we are going to have it, make sure that it is cold, and then we are going to weigh it again. We subtract the value of the volume, which, in other words, the container, and that will give you the weight or the mass of your unknown. How about the volume? The volume of the unknown is usually will take the volume of the container because it was gas. So what we do in order for us to calculate the volume of this flask, we are going to rinse it, fill it with water to the rim, and then we are going to transfer the water into a cylinder, and we measure how many milliliter is the volume of this flask. Once we are going to have the mass of the unknown, the volume of the unknown, we will be able to measure the density of this unknown. And from the whatever I showed you at the beginning, which is the calculation or the measurement of the molar mass of the unknown, because as you can see here, we have the mass of the unknown, we have the volume of the unknown. We will be able to calculate the density, and from that we will be able to calculate the molar mass of your unknown. So students are started to work on the setting up the apparatus, and they will start working on the heating of the liquid unknown. So can I have everybody's please attention, everybody, how to measure the volume of this flask? Because your vapor, like the liquid, when it is vaporized, it actually went all the way and it occupied the whole entire volume of your flask, okay? So after you finish with the second trial, everybody, after you finished with the second trial or third trial and you're done, you're going to rinse it, remove the stone, remove the foil, fill it to the rim with the water, okay? So that's what I'm doing. Tap water, any water. Fill it to the rim, okay? You see here? You see here? Everything is here to the rim, okay? Take this cylinder and then weigh. All right, this is more than 100. So we have 100. And then, after you measure the 100, this is 100, I throw it, and then I measure the rest. So the rest, if you look at it here, I have this particular one, 150. That is the mass, the volume of your conical vial, or like Erlenmeyer flask. After you finish the second trial, You want to measure because it's asking you what is the volume of your sample.
Yeah.
That's the volume of your sample, which is the volume of the Erlenmeyer flask.
Okay.
Because the gas will occupy its own container. Got it? Got it? So we're going to fill it with water and measure it with the cylinder. That's it. All right, that's it.